one of the big messages I had most of last year really was the fact that a lot of RAG systems and a lot of retrieval systems feel very much like recommendation systems, right? And if we can think about how we build recommendation systems, we can take a lot of that and bring them back into how we, give agents tools, build retrieval, and whatnot. And then when I talk about this idea of missing capabilities, a lot of it is the fact that these search systems don't really know how to do search properly, right? Like semantic search to me felt like my intern project in 2016, and then sort of everyone is catching on to what's happening now. But as Daniel will explain in basically the second slide, there's a lot more capabilities that exist in our disposal. For example, on Amazon, you can search for cheap shoes with like a 4-inch heel, right? Are those where clauses? Are those embeddings? Like, how do you do that? And then how do you do that across multiple modalities? And so that's why I'm really excited to invite Daniel to talk a little bit more about how he likes to think about these things. So yeah, Daniel, feel free to share your screen. Take it away.
Hey everybody, good to see you. Good to see lots of folks interested in doing information retrieval the proper way. And I want somehow for my setup here, I don't really see the chat. Actually, I do, okay. But yeah, if there is something that comes up during as I'm speaking, maybe Jason, you can flag it, and yeah, we'll
Good.
make sure to leave time at the end for sure. I'll try to do this maybe in half an hour and then half an hour for QA. All right, so yeah, how do we do search? How do we take learnings from recommender systems and apply them to our retrieval problem? And how do we use all our data to do it, right? Our data is the signal. How do we use this signal to improve relevance and have control over our retrieval results? I'm Daniel. I'm CEO of Superlinked. We have an open source product in this space, but I'll try to make this as least salesy as possible and just focus on how these things work. Okay, so just to set it up, let's start with a query. Let's take that as a problem statement. Imagine you have a travel company and you want to offer people AI-powered search, and people type in something like popular family-friendly hotels with good Wi-Fi near Manhattan Midtown. Wow, that's like topically relevant to where you are, Jason. Under 400. Let's set aside that probably under 400 there are no hotels in Manhattan Midtown that fulfill the criteria. But when you look at this query and you think about, okay, how would I do this? There is a lot of stuff that's going on in there. Think about each of these components as basically either a bias or a filter, right? So we either want to steer the results towards certain attributes or aspects, or there is an outright explicit intention to have like a binary, yes or no. So let's say popular would be like a numerical bias, or it could be popular to a certain segment of the users, and then it's not just one number, but some other representation. Family friendly might be something around categorical bias. And then, good Wi-Fi might be described in various ways in, let's say, the reviews of the hotels, and that's kind of like semantic bias. And then, of course, location in jobs or travel, a couple different areas, location is key, real estate, of course. And then there is that under 400 as a filter, right? So, if your toolkit for dealing with this is, let's say, just text embedding model under the hood, it's not going to actually understand all these different types of data, and you will just get poor quality results. So how do people deal with this today? It's something built around basically text to SQL, right? So if you think about it as kind of inputs on the left and then the query being generated on the right, you do have that conversational query. That's what we just saw there. But then, and now coming from kind of the recommender system world, we have some user context, right? Who is actually typing that query in, right? What has been their history? What did they click on? Where are they right now? And there might be some other context also, is it morning? Is it evening? All kinds of other factors that could lead into your eventual query being different, right? And one interesting thing to note is that this user context and other sort of contextual parameters are often actually not text, right? These might be clicks on some product IDs, let's say, right? So how, if the whole thing we have here in the middle is something that takes us from text to, let's say, a SQL query or Elasticsearch query, then you have to feed it text, right? And if you have a bunch of clicks, you know, how does that work? And then, of course, the problem of text to SQL is the latency, right? You might think quite a big SQL statement, or Elasticsearch queries might be hundreds of lines of JSON. So how is the latency on that? How is the reliability? If the SQL generation is too kind of unconstrained, it's going to generate somewhat unpredictably some queries that, let's say, actually fail in some percentage of cases, right? So reliability might be an issue. And then, at the end of the day, somehow you are doing the stuff on the left and you are generating a query that's obviously like compatible with your search system, right? So there might be some pre-filters, some boosting. Boosting is just a concept from Elasticsearch, kind of creating a combination of scores that then result in a certain item being ranked higher or lower. Of course, there will be your text vector search or image vector search in there. And then lots of focus these days on re-ranking, right? So like, the candidates we generated with the first 3 steps are not that great. So let's get a bunch of them and reorder them again. And then maybe once we see the set of candidates, we can have some additional rules for post-filtering. So, this is sort of what many teams in the industry, we mainly look at kind of the broader e-commerce, but in media, in knowledge management, this is what people are sort of working with and grappling and trying to optimize, right? But there is obviously a lot of issues all over this place. And, even if, let's say, you somehow figure out and you generate your query on the right, there are some things fundamentally broken about the search systems these days. And I'll kind of call out 3 things. So even if you figure out the left side of this, the right side still kind of sucks. And I'll focus on 3 things. Filtering today, I think, is used to approximate those biases, right? We talked about popularity bias or things like that. People try to model that with a filter. Like, okay, let's retrieve everything above 3 stars, right? That's going to be highly rated item. Or let's retrieve everything in, 10-kilometer circle around Manhattan Midtown. That's going to be a Boolean filter, right? But if you think about the underlying preference function of the user you are trying to model, the user is saying near Manhattan Midtown, right? If something is, 11 kilometers, but it's like fitting the rest of the query amazingly, then actually that would be a good result, right? But if you model these kind of biases, which you can think about some kind of like a sigmoid function, right? The user kind of prefers things in certain region, and then the preference kind of drops off. If you try to model that with filters, obviously you are using a very crude step function to approximate that smooth bias, right? So you'll have a loss there. So I think filters are overused. We should be thinking about mixing signals in a more smooth way somehow, right? So that's kind of one area that I think is problematic. Then the other thing is re-ranking. Obviously, re-ranking is a big topic. Everybody is talking about it. It's just such an easy way to put something on top of my existing retrieval and improve the situation a little bit. But when you think about it, and here, Jason, like I'm kind of curious what your take would be. But from my point of view, re-ranking is basically like if you could wave a magic wand and have a retrieval system that is the ideal retrieval system, it actually wouldn't have a re-ranking in it, right? Re-ranking is purely a hack of our underlying retrieval sucks, so we have to shuffle things on top of it, right? Like if the underlying retrieval actually worked and the 10 things that came out of the database for a given query were actually good, you wouldn't have to re-rank. And so nobody actually wants to do it, right? It's just some kind of hack we put on top because the first thing sucks and we are trying to fix it with the thing that runs on top. And obviously the issue with this is that when you re-rank, you are only re-ranking a tiny fraction of the overall index, right? Like if I have an e-commerce catalog and I ask for popular pens, and if a third of my catalog is pens, and I'm relying on re-ranking to kind of reorder by popularity once I get the pens out of the database, then I can't get a third of my database out and re-ranking by popularity, right? The re-ranking always applies to like less than 1% of your data. And so whatever you miss in that candidate selection can't, you will not fix that by re-ranking. And so pushing as many of these signals down into the underlying retrieval and then just getting the right things from the database in the first place should always be the goal that we have, right? And so that's category of issues that we see out there. And then the third category is that people try to kind of abuse text embeddings because those are the most widely available encoders for vector search. And in principle, you can make a string out of anything, okay? You can take a JSON object coming out of instructor, and then you can feed it all into text embedding model and get the vector out, right? This will not throw a type error. This will sort of like seemingly work, except the text embedding model that you use there really doesn't model the, for example, numbers included in that input correctly, right? Text embedding models understand numbers through how those co-occur in the training data. They get tokenized as strings, and then embeddings of those tokens get run through the network, and it's very noisy. And there's like easy ways to figure out just how noisy. If you just stringify some integers and then make embeddings of those strings and calculate similarities between those vectors, you will see that there is no like underlying concept of like 49 is 1 less than 50 in the latent space of the model. And so stringifying non-text data and running it through text encoders, that's another like big issue that exists out there. So these three things are basically kind of the what is wrong with like the left side of the previous slide, right? We had the what just happened? We had the previous slide, we generate the query, is great, but actually the query is problematic also, right? Because it has all these issues. Okay, so what should we try to do instead, right? In principle, somehow we should figure out, we should still have the same inputs on the left. We have our text query, we have our user context, we have our other context. And ideally, we should have some kind of box that converts that into pretty much two things. We should stuff all the signals we can that look like that bias into a vector. And if there is explicit filter content, or if we just need to filter the results based on access controls and so on, we should also generate some filter predicate, right? Like all these other things, ideally, you are not doing. So boosting is done within the embedding. Re-ranking you don't have to do because now all your signals are in the vector and they feed into the ranking. You don't really have to do post filtering. You do the pre-filter for access control and so on. So this should be sort of the ideal output of your kind of query understanding system. And then we have the vector databases where they're pretty good at like vector search and filtering, right? So they can do that for you. And then the other half of the problem is how do you take your data on the right side and make these vectors that again integrate all these signals so that then in the middle this thing kind of aligns, right? So you need basically a couple of these orange boxes to do that. And then somehow there needs to be also a concept of the feedback, right? So I think Jason talks a lot about feedback loops. Like, there is the behavioral data. Companies have all these clicks and all these feedbacks and all of that. Somehow that needs to be feeding into basically both of these boxes, right? How to close that loop and actually improve this over time. Okay, so am I sort of like making sense directionally, Jason? Is it? Yeah. Okay. And okay. So cool. So now basically the rest of the problem is like, okay, how do we make these orange boxes, right? Like we have figured it out. We just need a way to do these transformations. And this is where I think in the sign up for the event, we call this encoder stacking. Since then, I started to talk about it as a mixture of encoders. It's basically the same thing. But this slide is like experimental. Let's see if I like confuse people more than not. But basically, one property of a system that actually makes this work is that it can't just be based on text encoders or language models. You need some other little transformation boxes that can take things like latitude, longitude and make an embedding, or things like a number and make an embedding, or have some interaction data between, let's say, products and users, or users and answers. And somehow you need to be able to take that signal and make an embedding out of it. And this is what we call these encoders in the middle. So just running you through the picture, basically, think about the conversational query coming in. It's basically a string, right? And what you have to do, similar to how a mixture of encoders would work in an LLM, where there is some component up front that splits the query or reformulates it for the input of each expert within a MOE model. Here we are kind of doing the same thing. So there is some DSPY style optimized prompt that takes that query and feeds each of these encoders with the appropriate input. Okay, so for like numerical encoder, if there is something like popular word mentioned in the query, it would tell numerical encoder, okay, let's create this kind of bias towards popular things in sort of in the sense of a number. If there would be a mention of Manhattan Midtown, it feeds location encoder with Manhattan Midtown as a string, and that encoder is trained to take that and produce embedding that, let's say, approximates travel distance by car between different places, right? And it's, you know, the basis of that is something that understands a map, right? Is not trained just from like internet data. You know, the graph encoder that captures the, you know, which products are interacted with within the same user session, that will be some kind of graph embedding, right? That we have to train on the on our specific data. And again, it has nothing to do with the language model, really, right? So basically, we break the problem down into kind of Lego blocks, out of which we assemble a model that has the right encoders that fit our problem, and then we put a prompt optimizer in front of that feeds those encoders with the right inputs given the query, and it also sets the weights for how the outputs of those encoders should be aggregated into the final embedding. And just to be like super clear, this final embedding will encode biases towards location and numerical biases towards popularity and semantic biases towards you know, family-friendly, whatever, good Wi-Fi hotels, right? All of that signal will be compressed into the embedding that comes out of this machinery. Kind of makes sense. Too out there. What are we thinking?
We'll do some questions at the end. I think some people are curious about the DSPY style prompt.
Okay, cool. And then, you know, to kind of complete the picture, okay, so we have made a vector that encodes all these different things that appear in the query and does it kind of natively because those encoders understand those things. And then, you know, user context, let's say, is a user embedding that somehow also captures those interactions, right? It could be accumulation of embeddings of the items the user interacted with, for example, right? So this might be like pre-computed for each user, and then to answer a given query, you fetch that out of a database. And the same for the other context. So the kind of uniformization that we are trying to impose on this is that each of these pathways makes embedding and, let's say, a filter predicate if needed. And then we have another aggregator on the back of that somehow merges all of that stuff. And then finally, the last dot here is a vector with some filter predicates that compiles all these signals together, and then you just send it to a vector database and do the lookup. Okay, and again, some of these encoders are pre-trained, some are unsupervisedly trained on the specific data set, some are, you know, we have like a couple text and image embedding fine-tunes based on the domains in which we operate, and then you know, basically Superlinked is a framework to kind of build this orange thing, right? So like all the orange stuff, we have an open source framework for that. And obviously, then on the other side, you need to be feeding the vector database with your data encoded with similar machinery, so that the vectors that the search vector meets the data vector in the database, and everything is kind of compatible. Okay. Now, in terms of like cloud architecture or component or system architecture, let's say, the way to think about it is that you have like data on the left, you have your encoder library, let's say, on top. You have your vector databases on the bottom. We work with Redis, Mongo, and Quadrant. We are adding more, but we are pretty slow on that because we actually need those to be battle tested. Like we operate in kind of low terabytes of index sizes. So when we launch a connector, it's not like a community contributed connector. We work very closely with the core engineering teams of all those companies to make our thing work with their product. And you can kind of use them interchangeably. So Superlinked wraps not only the read and write APIs of the database, but also the management APIs. So you can kind of switch and explore between them different kind of cost and latency trade-offs, basically. And then on the right side, you basically put up API endpoints on top of which you can build retrieval for RAG and recommendation systems and search, and people do all kinds of analytical tasks as well. Because think about it, now you have vectors that compile everything you know about the whole entity, right? Everything you know about the user, you have an embedding for it, like all compiled into one embedding. Same for products or pieces of the knowledge base and so on. So we try to then make it easily kind of accessible through APIs, so you can build on top of that. Okay. And then, case study wise, just kind of motivate this. We have like one of the things we published is with the jobs marketplace, they got 50% lift in people applying for jobs. This replaced Algolia in this case. And what I want to call out is that Superlinked is not really a search system. It's just like helps you build stuff with embeddings, and that means that you have a lot of flexibility. So this company built a bunch of tools for the people listing the jobs on the marketplace and finding people, not just people finding jobs, right? You have a lot more flexibility because we don't bake like just search specific stuff into the APIs. And then similar case study with a fashion retailer that increased, they added more than $10 million to the bottom line when they started to work with us. And then I'll mention something about evals. I don't know, Jason, to what extent you focus on evals in the course, but basically just the TLDR is that a lot of the benchmarks out there, so you might have seen this MTEB, the embedding benchmarks table, and Bayer. All of these things are text data and to text query evaluation, right? And this is like super not realistic because in reality you have a product in a marketplace has 50 properties and maybe a couple of them will be textual, but everything else is like some other metadata. And so all of these benchmarks are kind of not really fit for approximating production performance from our point of view. That's kind of a bummer. And also the results on these are not that good. Like these scores top out at like 0.6 for state-of-the-art models, because all the models that are being evaluated here are purely text embedding models. So that's like the somehow information retrieval benchmarks are stuck in this local maximum. And we have been working on data sets to kind of fix that. There are some other efforts out of Stanford that are kind of trying to add more metadata and more kind of realistic looking data sets. But yeah, we are very early in that respect. And of course, making data sets is hard because the traditional methods of how you generate candidates and then label them with the LLM work with like text retrieval methods. And so that's the same kind of issue. Like you are trying to measure a system that doesn't just work with text retrieval methods, but all these other things. So it's a little bit of a chicken and egg, and then you have to score way more candidates with an LLM. It can be expensive. So, I mean, that's kind of part of why this is stuck. And yeah, I'll kind of pause there. Just as a summary, we have an open source, free to use Apache 2.0 framework on GitHub that allows you to do a lot of what I described. You you can run that yourself. We know of a couple companies actually running this in production in like decent scale, 100,000 items, tens of thousands or maybe 100,000 queries per day kind of scale. And then we have a cloud product that we work with companies more hands-on, where we have some proprietary tech to scale this up to like 100 terabytes of click data and millions of queries per day. So I'll pause there. Questions? Very happy to share anything people are interested in.
This was great. I also really like the fact that there were no adjectives. Everything was just like numbers on scale, and that's I just want to call that out as something that's really appreciate that.
Yeah.
Everyone told me is like it works at large scales, production ready for the enterprise, but hearing like low terabytes is kind of a fun flex in that.
So our biggest vector search index we have ever operated so far is 2 terabytes. And our biggest input data set that we ingested is on the scale approaching 100 terabytes. And this is actually interesting that you hear about this unstructured data taking over the world. When we start working with the e-commerce company, the product catalog is maybe in the hundreds of gigabytes, right? Text and images and all that. And the click data is potentially 100 terabytes. So I don't know where which dashboard people are looking at, but I see there is way more clicks than text and images in the data warehouses of these companies. So, and if you don't use the data, right, this is a problem because that's where the signal is, right? And that's the lesson from the recommender system world, right? Is that if you don't use the behavioral data, if you have been on TikTok ever, then you understand that this is something that you absolutely have to use to help your users converge to what they are looking for.
Oh, I guess before I ask the big question, I'm personally curious. Like right now, we're kind of doing these specialization because we need different encoders to do different things. What do you feel is the timeline on sort of even this part of the stack being better lessened away? Like at what scale will we not need these kind of tools, or is it going to be the case that we're just never going to get there in the near term?
So are you saying at which point a text encoder can replace the specialized encoders, basically?
Or even just, maybe it is just a transformer that takes in the click data and queries in, and that's all we need versus actually having to specialize and this being sort of a durable architecture. I just saw some papers recently on using transformers and item embeddings and stuff like that.
Yeah. I think there is a trade-off in, can, maybe Stitch Fix or YouTube, can YouTube train a transformer on their click data that will outperform everything? Probably yes, right? That's probably the answer. Can an engineer in a company that wants to solve information retrieval problem actually solve that problem with reasonable cost and time to market and all of that? I would hate for the answer to that to just be use this black box thing here. I think it's much better for that engineer's career and also actually in terms of performance to have some kind of toolkit that allows you to assemble something that's a bit more specific to that company. Because because if you take your thought to the extreme, then there is also no companies, right? Because so I for now I operate in the world that first party data is a thing, and companies are capturing this data, and they have slightly different user experience they want to build and slightly different business objectives, and having a way to express that into a retrieval system is how you basically get the edge until AGI takes over everything, and let's talk in I don't know, a couple of years, and maybe we'll be all sitting around the campfire thinking back about the times we still had to work. I don't know, right?
I think everyone has different AGI timelines on that kind of stuff. Cool. Let's jump into some of the upvoted questions. So the most upvoted question was, can you walk through the SimHo12 query example and tell us what Superlinked will do to help you service that query?
So let's remind ourselves the query. Yeah, so basically think about it as, with this specific client, the hotel, the specific client is not Booking, but it's a similar company. So let's take Booking as an example. Think about the data that Booking knows about the hotel, right? It will be a bunch of reviews. It will be all kinds of metadata. There will be some categorical properties. The categorical property of like amenities might have a cardinality of 10,000 things that potentially can be turned on. And yeah, there will be, of course, location data, and there will be images as well. So that's the data set and prices, of course. That's the data set we are working on top. So you would basically go and create a superlinked index for hotels where you would have your data schema of like hotel review and user and clicks. It starts with a couple of Python classes with like typed properties. And then you would create an index for hotels where you select these encoders and bind them to the different properties of those input objects. And then when you push the data into the system, those encoders are used and their outputs are aggregated to make, let's say, hotel vector. Okay, so this is the data ingestion part. And then when the query comes in and you get this kind of text from a given user ID, right? It gets basically broken apart into like, okay, popular, and that gets pushed into the, some kind of popularity counter encoder as like, okay, we need positive bias on this dimension. Family friendly, we have a categorical encoder that is not like a filter, but it creates bias towards, there is, you can do like multi-hot, but then like high cardinality categories need something a little bit different. So again, there is an encoder that gets kind of prompted towards creating positive bias towards family-friendly like categories. And again, like with location, there is a location encoder, right? That on the data side ate all the lat longs of all the hotels, and on the query side can get prompted with the text location and make an embedding that such that the cosine similarity in the search afterwards approximates some kind of travel distance between places, right? And then under 400 generates a filter predicate in the superlinked DSL, basically. So somehow this all gets compiled into an embedding that expresses all of those biases plus the filter, and then that gets sent to the underlying vector database to get the 10 hotels that are family friendly and have good Wi-Fi and whatever are popular. And then without any re-ranking, that's the 10 hotels you get out, right? I also mentioned we have some custom fine tunes. For example, one fun learning is that for text embeddings, it's actually worth it to do text embedding fine tuning. You can't fine tune text embedding model to understand addresses, right? That's not what I mean. I mean things like, for example, this adjective noun association. So good Wi-Fi, if you just take like whatever MTEB winning text embedding model and you give it a bunch of reviews, and some reviews will say bad Wi-Fi and some reviews will say good Wi-Fi, and then you search for good Wi-Fi, you get a mix of both good and bad Wi-Fi's out, right? Because the model over-indexes on Wi-Fi, not the association of good Wi-Fi, right? So, for example, we have fine tunes for that, right? So, like this sentiment-aware text embeddings for reviews and things like that. But that's like tiny part of the puzzle. Hopefully, as I now kind of explained, that there is no amount of fine tuning you can do to understand like something like numerical bias. And that you can find out by just trying to understand how numbers are represented by the text encoder and how they are tokenized as strings, and how embeddings of those tokens like roughly approximate the actual numerical value of the number, but only roughly. And so there is space for text embedding fine tuning, but the applications are limited to actually eating text, right? And a lot of this is not about eating text.
And I like the example of good Wi-Fi. I feel like, in the course we talk about this, like, okay, if you build like a dating app, it's like, is I love coffee and I hate coffee the same thing versus I love tea? Well, it's not actually whether or not this is similar, it's whether there's actually some other outcome that happens at the end, whether there's like a match or something like that.
Mhm.
So I think it's another good example.
Mhm.
One of the questions I think is also pretty relevant and something I'm very curious about, which is how often do you refresh embedding models? I feel like
Mhm.
at Stitch Fix, retraining and keeping these things stable was like a whole part of research. How does
Yeah.
Superlink think about that?
Yeah. So uh, if you train an encoder, you take all these inputs, you feature engineer all these different types of data, you make a custom encoder like a two-tower model or some other kind of training policy, then kind of distribution drift on any of those properties forces you to retrain the whole thing, right? This is a problem, and it can happen, as often as distributions on any of those things like meaningfully change, right? This is of course specific to the given case, and that's kind of one of the benefits of not doing that and instead doing this kind of composition of encoders, because if you do have to retrain something, it's going to be one of those boxes in the middle, not the whole thing, right? Uh, you can selectively update parts of your model this way, and like save yourself a bunch of trouble. That's kind of one thing. The other thing is, as your data changes and you have to re-encode, right? Like let's say popularity of the hotel changes and price doesn't, or price changes and description doesn't, right? Do you have to take the whole entity and re-encode the whole thing? Or can you rerun like one pathway through this and update, let's say, the embedding signal of the location and then aggregate with the rest of the outputs? You can think about like caching on the individual encoder level, for example. So in terms of data updates, this is kind of breaks it down into more manageable components. In terms of retraining, it also means that you can think about retraining individually for the components. Yeah, and then how do we detect that the retraining is needed? I think the more you can productize the retraining and just kind of do it, and it's not too expensive for the individual components, I think it's a good idea to do that. But if it's like a big retraining operation, then yeah, you'll have to be more careful about like measuring. Okay, now the distribution have drifted, and all our embeddings are clustered over here, and we are not actually using the space. And so let's like retrain to kind of stretch it out and identify the meaningful structures in the data again. Right? I can like keep talking about this for a long time. I'm just wondering, is there anything else coming up? I see.
Hey,
Lots of
Danielle.
folks.
Looks like Jason got kicked out somehow. I'm gonna just pull from the Slido questions. How often do you refresh each embedding model? Seems like there's a lot of overhead involved.
Yeah, I think I just did that one.
Oh, yeah, sorry.
Yeah.
How about keyword heavy query? User is looking for a GUID.
Mm-hmm. Yeah, so if you are looking for like exact matches, then that's for me that's a part of the filter. Yes, there is a caveat here that I totally skipped, which is sparse data structures, right? That's kind of a world that you either force it to be a part of your filtering mindset, right? Because this is kind of filters, right? Like I'm looking for this exact thing somehow. So you either kind of stack it into that part of your stack, or you think about these encoders as either producing dense or also sparse representations, and then kind of it's more part of this situation over here. Once vector databases will be a bit more flexible about having like composition of sparse and dense representations and queries, I think we can treat it more like part of this encoder side of the world. For now, we treat it more as a part of the filter side of the world, at least in our product. So like keyword filters in a way. And we use the, underlying kind of sparse indexing, BM25E machinery of the underlying database for that.
Can you talk more about how the encoders should be designed and then in turn how that is combined with the functioning of the aggregator?
So, I mean, encoder is really just some sort of input and some kind of dense representation output. And then the aggregators get weights from the LLM that does the query understanding, or you can actually train a weights model separately. So you can have a model that, given a query, you train on your click data and it sets the weights. And then the aggregator can have all kinds of different forms. The most simple thing you should think about is just you kind of unit normalize the encoder outputs and you dimension-wise concatenate them into a big vector, right? This would be your kind of starting aggregator strategy, right? The cool thing about that is that the signal is encoded in separate, ranges of the dimensions, which helps explainability on the query side. And also it allows you to do the weights at query time, right? I can scale different ranges of these dimensions differently. And then the search vector can express, okay, I actually care about this signal that much more than this other signal. So it's like query time weights on those components. The same way that like mixture of experts model would score the outputs of the encoders before it aggregates them. And then maybe I'll just say one more kind of tidbit, which is we do a lot of vector aggregation. So like whatever comes out of here with the user context vectors and so on, we do a lot of like averaging and aggregating and time decaying between embeddings. And we notice that it really matters how the encoder is trained versus how, let's say you average 10 of those embeddings together afterwards, how well does that represent the data in the 10 source vectors? And rule of thumb, the more efficient the encoder, the kind of less well it responds to this aggregation, right? Because it's already very efficiently encoding stuff in very few dimensions. If you average a bunch of those things together, you will basically destroy the information. And the more sparse the encoder is, all the way to, like bag of words or whatever, the better it responds to aggregation, because it's literally like union of keywords that appears in the document, right? So that's the ease of aggregation scale. Like very sparse aggregation is meaningful, very dense aggregation is hard. If you can train some sparsity into your encoders, then the aggregation will survive. So like if I aggregate a vector that represents apple, car, and motorbike, somehow all three signals will still stay expressed in the averaged vector, as opposed to being some point in the middle of those three things that doesn't mean anything anymore. I hope that
a lot of the learnings we had at Stitchfix as well. So it's kind of cool to sort of see this come up again. I do want to ask one question, just as I saw this like on the in the questions, like, and in my opinion, it's maybe like a spicy question, but what are your thoughts on using things like graph structures and graph retrieval when it comes to these things? Like I think I've personally been very embedding pilled for most of my life. But I'm very curious where you sit on this ideas.
So we kind of see graphs as one of the inputs, right? I have a graph encoder on here. I think it's somewhat of a stylistic debate, like what's the steering wheel and what's the car, right? Is graph the input to the embeddings, or is graph kind of the master data structure and then we hang the embeddings off of the graph nodes, right?
Yeah.
But yeah, so from our point of view, graphs or just users clicking on things and through that making an implicit link, right? This is a useful input. We want to use that in our representations. We train these graph embeddings and aggregate them with all the other stuff. And then, when people talk about graph rag, I think they also talk about like post-filtering of the results by traversing some nodes. So maybe like using vector search to discover the interesting graph nodes and then expanding to neighbors, and then that's the result, right? So, but that expansion, if you do like one hop neighbor expansion, it's basically, you can do a SQL query for that. I think like graph database is useful if you want to do very long traversals or calculate some more, harder to calculate graph metrics like node centrality. Like if you really care about that, And if you want to have a data structure that you can update a lot and then high kind of throughput identification of some connected components or whatever, then okay, graph database is useful. From our point of view, graph is the input. You should have it as a part of your encoder portfolio. And yeah, the rest is kind of filtering.
Makes sense. I think we're pretty aligned there as well. Great. I mean, there's only 10 minutes left. And this is the question I kind of generally ask everyone, which is,
Actually,
what do you think is a question?
Sorry, so I think there is like one more kind of just landmark on that landscape of your previous question. You know, people generate these graphs with the LLM basically, right? Or they kind of have a language model generate graph queries or inspect the results of those queries and then make more queries. One thing that's to be kept in mind there is if your nodes in the graph have a bunch of metadata that's not textual, right? Numbers and so on. And you are using your LLM to kind of navigate the process of doing some retrieving, looking at results, whatever, call it agents, right? The main thing I want to get across is that the pilot of your airplane sees the whole world as string. This is like fundamental problem, right? Because a lot of the, let's say, metadata on your graph nodes or otherwise are not strings, right? So you're using like a pilot that's like stringifying the world and then processing it, right? And I see, information retrieval as a way to kind of connect that pilot to sets of data that are actually not text. And the link there has to be encoders trained to understand this other kind of data, right? And that also goes to, will it all be just LLMs at the end of the day? I don't think so because of this, right? That basically there is some way you have to process other kinds of data, and maybe that other way doesn't even have a tokenizer, right? It is some other way to feature engineer the
Yeah, the moment you said this, like pilot sees the world as a string, I just go back to the example where like every LLM thinks 3.11 is bigger than 3.9.
Yeah. And that's just such a tiny, maybe example of the overall problem, right?
Yeah.
Like it's such a, just like a little gateway. And once you start going down the rabbit hole, you'll discover that we have been to some extent lied to, right? Like, actually, this is like very poor way to see the world. Like you can't really stringify things, and that can't be the end of this, right? So yeah, I encourage people, take some embeddings of stringified numbers and go play with that and become like even more embedding built in a way.
Yeah, I mean, there's a joke that I used to tell when I was doing like a lot of like embedding work. It's like, you ask AI what's 10 plus 10, it says 16. You say, no, it's 20. And then you ask it again, it says 17. You ask it again, it says 18. I mean, in the limit, you'll get the correct, but, until you get to real AGI, you still have to just sort of hard code a couple of these filters and get things to work properly.
It's a very expensive and slow way to get unpredictable results, right?
Yeah. I like that you're also down the whole path of like using a lot of metaphors to explain these concepts. Well, the last question I like to ask everybody is, what is something you feel like we are not asking? Right? What is something that is sort of missing in sort of the ways that we in general have been thinking about these kind of systems?
Yeah. So I think this whole we have to look at the world through other lenses than text tokenization. I think that's one of my big ones. The other one is the re-ranking, right? Like I think re-ranking is overused. All the re-ranking models out there, pre-trained, cross-encoders, or actually also the late interaction stuff. Like I want people to understand that that's all text operated also, right? Like it, tries to address issues that I think should be addressed in the underlying retrieval and is denominated in text, right? Both on the query side and on the data side. So that's maybe extension of the first point, but yeah, re-ranking is kind of abused, and it's just a function of how easy it is to add on top of an existing system. So I think let's take a magnifying glass and look at our re-ranking, and then the filters is the other thing. Like if you are generating from a text query some kind of insane filter predicate that actually should be smooth biases, because that's the underlying preference function of the user or of the system doing the retrieval, right? We have all seen like this Venn diagram in high school that like if you intersect too many of those circles, the middle point is like very small. And that's what you are doing when you stack a bunch of Boolean filters, right? As opposed to creating some mix of some distributions that add up to kind of the results you want. So less filtering, less re-ranking, and less just using a text embedding or text understanding model for what we do. I think those are my three sort of commandments.
Nice. Yeah, I think we're definitely going to move towards a world where maybe in the future there are encoders that can handle all this data, but not as text. But yeah, I think your example of just the pilot sees everything as a string is sort of a big issue. And even though there might be things like visual language models that can now have like image tokens or audio tokens, those modalities are still quite broad and that don't really cover the information retrieval use cases that are specific to many real problems in the industry.
That's right.
It's
And
not
you
just
should
fetching
combine these
GDS.
things together, right? So I'm not saying text embedding bad. I'm not saying call poly bad. I'm saying that's good for that part of the input, but we have all this like other data and we need to integrate it somehow to get the maximum kind of signal and edge out of it in terms of quality of results, in terms of the control we have over the results, and so on. And yes, like, I encourage everybody to check our GitHub. Again, it's free. Well, maybe it's not free because you have to give it the GitHub star, right? So it's like proof of work kind of thing.
We will make sure that everyone gets the email and we'll make sure the link goes directly to the star tab.
Perfect.
We'll share the slides at the end. We'll share some study notes once we generate those. And, expect an email sometime tomorrow with everything that is mentioned in this talk. And Daniel, really appreciate this. I think this metaphor of the world being seen as a string is a big one. And I'm excited to hear more about what you guys are working on.
Thanks for having me. And good luck, everybody, with the course. And see you out there.
Awesome. Take care. I'll follow up over email.
Cheers.